Thanks, Mr. Chairman, for your introduction. So this work is co-financed by the French Ministry of Defense. So first, I'm going to quickly introduce the subject, then I'm going to present the proposed electronic nose prototype we worked on, and then the experimental setup and the results we obtained with this prototype. So first, chemical warfare agents are very dangerous compounds which are commonly regrouped in these 4 categories. Perhaps the most infamous and lethal one are the nerve agents, such as sarin, taban, and so on. The objective when we want to detect these is to have a low-cost, fast detection of these compounds at a low concentration in a very complex environment. The atmosphere is composed of nitrogen and oxygen, which will not interfere with some sensors, but also with water vapor at various concentrations, and several types of hydrocarbons at various concentrations too. So existing technologies to detect those are portable spectrometers, which are expensive, bulky, have specific response, and allow detection at low concentration, but since they are massive and expensive, they are not really, they are only used to confirm the presence of dangerous compounds when we suspect that they are dangerous compounds, and we want to have a use case where soldiers may have a very small wearable sensors to have this detection in case of surprise attack. So this is why we're working with an electronic nose solution, which consists of an array of very non-specific sensors and a data processing algorithm to have pattern recognition. These are more cheapest. These are compliant with wearable applications, and this is why we're interested in them. So the proposed electronic nose system is the following. We have a sensor array composed of functionalized multi-wall CNTs, carbon nanotubes. So these are polymers deposited on interdigitated electrodes. These polymers and nanotubes are making a very randomly composed nanocomposite on which volatile compounds may form non-covalent bonds. This might change the tunnel conductivity between the nanotubes, and this is measurable as a complex impedance variation between the electrodes. We assessed, thanks to the literature, that 6 to 10 sensors are enough to have good cross-selectivity for the sensor array for specific applications. So we manufactured 7 different sensors in order to discriminate polar molecules, broad hydrocarbon response, and to also have a selection between hydrocarbons depending on if they have aromatic groups, alcohol groups, and also if the molecules have the phosphonate group, which is the one composing most nerve agents. So this is what we want to detect. So 3 of the 7 sensors have been added with this polymer. Once we have the sensors and we expose the gas on them, we measure their resistive and capacitive signals, but we assessed that the signal to noise ratio for our sensors was better for the capacitive signals. So this is what we're going to talk about from now on. We extract 7 features per sensor, steady state and dynamic sensors, in order to have a broad range of features to feed the classification algorithm with. So now I'm going to talk about the classification algorithm. Many classification algorithms are used in the literature, such as support vector machines or artificial neural networks, and in all of these literature papers, this algorithm works at best because it's really dependent on the database they are trained with. So we had to use different algorithms and test them for our own database. and SVM was the most accurate in our case. So basically an SVM machine, a support vector machine, places, you have your training database, the supervision for the training place the samples from your database is in an n-dimensional space where n is the number of features. Then you it trains to find an hyperplane in this to separate the samples because it's supervised, it knows which samples are from which gas, if it contains or not the nerve agents. Then it finds the samples the closest to your hyperplane and measures the distance to the hyperplane. And so it finds an hyperplane which maximizes this distance. That's your maximized hyperplane to have the biggest margin between the classes. Then you can test your algorithm with new data, which is unknown data, and depending on which side of the border they're on, the classification algorithm knows if it's your sample contains a nerve agent or not. So we implemented all these things, the sensors and the algorithm into a custom-made electronic nose, which uses free electronic device from the commercial electronic device. The measurement is done thanks to an ADI analog device component, which multiplexes the 7 sensors, and the algorithms are implemented on a Raspberry Pi here. All of this is very low cost. It costs less than $50. It can be wearable. It can be input in a case which would be a smartphone size and smartphone weight, and would require only a smartphone battery to be used for 14 hours, thanks to the 2.1 watt power requirement. Sorry. So we wanted to test this prototype in a realistic-ish environment. So we filled 2 Tedlar bags with different atmospheres, with different gas mixtures. Both bags are filled with a complex gas mixture containing dry air and water vapor at 1000 ppm and a very complex mix of different hydrocarbons, which simulates our atmosphere with humidity and pollutants. In one of the 2 bags, DMMP was added, which is a very commonly used nerve agent simulant, because we obviously don't work with nerve agents. So we sampled 24 samples per bag with an absorption cycle which consists of emptying the bag at 100 milliliters per minute, and then cleaning the sensors with dry air at 500 milliliters per minute. And we've done these exposition cycles from the 2 bags in over a week, and with changing the order of exposition in order to avoid training bias for our classification algorithm. To further avoid classification algorithm training bias, we use a stratified k-fold cross-validation. So these are our 48 samples containing the DMMP, so nerve agent simulant, or not containing simulants. The first part of the stratified k-fold validation protocol separates these 48 samples in k subsets. Here we chose 8 randomly in order to have as many samples from each class in each subset. Then 7 out of the 10 samples are used for training the algorithm, and 1 is left for testing the algorithm. And this is repeated as many times as needed for every sample to be used for training and testing. Then the algorithm average the result of the SVM over the 8 folds of the cross-validation protocol. So this is very useful since we have a database of 48 samples, which is good, but could be better if we had maybe 48 more, 200 samples, but allowed us nonetheless to have an accuracy of 98% with our SVM. It's very interesting to note that we have a very complex mixture with 7 pollutants at 1,000 ppm, while the molecule we want to detect was inserted at only 1.6 ppm, so very small amount of molecule in a very complex background with more and more, biggest concentration of other pollutants. Compared to other works, this is good because most works in this field usually work with a simple binary background here, and in all of these other studies, usually it's only characterization studies where the response for the DMMP is assessed, then the response for one pollutant is assessed, then for another one. Here we try to mix everything up to test the system in a realistic-ish environment. So we propose a low-cost electronic noise detection for the for our chemical warfare agents. We had reached a very high classification rate, and all the technology which are used are compatible with further miniaturization, compatible with wearable application. So for perspective, we want to confront this system to a broader set of interference and complex mixtures and implement this on FPGA to further decrease the power consumption. Thanks for your attention, and please let me know if you have any questions.